Yeah. So the question is the mechanism for squeezing the tail. So it turns out that the tail and perineal area have afferent, sensory afferents, that actually go all the way through the entire lumbar margin. And it turns out that the escape response in a rat can be triggered by tail afferents. They can't look back there, so they use their tail as a signal, and therefore those afferents are really important and a strong driver of the locomotor generator. So that's how that works. They don't know if it's exactly the same in the human. Of course, we don't have a tail, but we do have perineal afferents. And there are people out there studying that aspect. Other questions? Certain questions.
It seems like there's a disconnect in the earlier slides, just training by tail squeezing or by swimming, and they're able to learn, but then when you put them on the ground, they're not able to learn. So it seems like a disassociation between the stimulus and the pattern generator. So have you ever tried doing one training routine and then switching to a second training routine to see if they can learn faster in the second case?
So our thoughts about how rats recover function is basically they're going to recover as much function as you challenge them to get. In their cage, there's not a lot of impetus to show more than rudimentary walking because they're going to be able to get around to get to their food and get to their water. There's a guy named Martin Schwab over in Europe, and what he did was he basically built a rat condo, and they had to be able to go up and down stairs and go through tubes and go across ladders in order to get to their food and their water. And he was able to show that there was a difference between that and having the animals housed on just a flat surface, but with the same amount of area. So I think that the spontaneous activity in their cage is sufficient to get recovery, but it's only going to go as far as you challenge the system to go. Does that make sense?
Yeah, I think so.
So in cats and in human, we think that the level of excitability in the spinal cord may be a little bit lower than in the rat. And that's why things like epidural stimulation and magnetic stimulation, they're using now magnetic stimulation of the spinal cord, may be necessary to get that pattern generator going. But there's also this huge divide between acute, which is what I'm always talking about, and chronic. If you wait until the chronic phase, things are very different. Other questions?
I have started doing some research on the flow of cerebrospinal fluid.
Yes.
And I'm wondering if the flow of CSF in the injured spine has any effect on recovery.
So the question is about cerebrospinal fluid flow and whether that has any influence on recovery after spinal cord injury. That's a complex question, but I will answer it this way. The difference in the space available for the rat and the human in the column is quite substantial. So we do believe that in the human, the swelling that occurs in the spinal column is sufficient to not only block cerebrospinal fluid flow, but also blood flow locally. So ischemia probably plays a larger role in a human injury than in a rat injury, because the rat has more space relative to the size of the spinal cord. Having said that, it's probably not a huge contributor. It's probably a contributor, but it's probably not a huge contributor. And the reason I say that is even in a, so this was research that we did years ago together with some of our neurosurgeons. Even in a very swollen rat cord, if you inject a tracer or a dye into the spinal cord, there's still cerebrospinal fluid flow. And it goes from the central canal out, and if you inject close to the central canal, you see this beautiful track of the tracer going out, even when it's swollen and it's compressed in the canal. And we did a study where we actually put little wedges in to provide compression, and there's still some flow. Exactly what it means for the human, I'm not sure. Any other questions?
You showed videos where you had, the rat wasn't able to alternate in when it was walking, but was able to alternate in water.
Yes.
And you said it might be because of the sensory input that it was getting.
Yes.
Was there a difference in the speed of movement? Because I would assume no difference at all?
No. So the graduate student running that project has analyzed this data, I mean, it's just to death. And one of the things that's really fascinating about the data is it's not dependent on the speed of the animal or on the speed of the paw during the stepping or swimming. Because that was a question that came up. So I've given this talk in a couple of places that they have a lot of CPG people there, and that definitely came up. But it's almost as if we've been able to manipulate the alternation without changing anything else, which is really very surprising. And the people that model the system are pretty freaked out by this because they've never even considered this as a possibility. Alternation has always been integral with the actual rhythm.
Have you done the water walking compared, which is more like swimming now walking?
Nope. Do you mean with the silencing?
Yeah, the alternating versus not.
So one little wrinkle that I didn't talk about, but might be of interest, is when we see this disruption in alternation, we call that the phenotype. Okay? We only see the phenotype when the animals are walking A to B. If they're whisking, if they've got their nose down and they're whisking, they don't show the phenotype. Okay, so what gives with that? So the way we interpret that is how much brain control is going on versus how much autonomy of the central pattern generator and the spinal cord. If the spinal cord is stepping autonomously, if the brain is just saying go and leaving it do it, letting it do its thing, we see the phenotype. So so for instance, we sometimes put the animals on a ladder and we don't see much of the phenotype because they're really paying attention to what they're doing, and it's top-down control, it's brain control. And I think that's probably what we would see in shallow water, but we haven't tested it. That's a good question. One piece of data that I didn't show you because the slides went kaput is we also don't see the phenotype if they're walking on a slippery surface. And we think that also indicates brain control. If they're unstable, there's more top-down control. If they've got great stable footing, we see the phenotype. Any other questions?
All right, let's thank our
Thank you very much.